Hello, Flat Earth researchers, debaters, and debunkers. If you are ardently defending the globe and becoming increasingly frustrated with Flat Earthers, maybe you are not seeing what the Flat Earther sees. And perhaps you are convinced that the numbers cannot lie when it comes to proving the globe with geometry. So we'll look at how those numbers can be manipulated. But first, let's have a look at perspective and how horizons are a personal perspective. Here we can see that the horizon is at the eye level of the camera, the person behind the camera taking the picture, not the eye level of the person standing in the picture as if he is holding on to the sun. This is a great example of how perspective works, because if you've ever tried to take one of these shots or partake in a shot like this, you will know that if you are the person standing in the foreground, pretending to hold the sun, you yourself cannot hold up your hand in the right position. You have to be instructed by the person behind the camera to get the hand position correct. So in the same way, this man in the shot, apparently holding the sun in his hand, sees a different horizon to the one we see through the camera. His horizon will also be at eye level, and because he's higher than our eye level, then we have to draw a horizon line for him here. So the yellow line is his eye level, and that is where he will see his horizon. Of course, he's seeing pretty much the same thing. His little bit of extra height there won't make much difference, but it does to this particular picture, because just as we see, in his eyes, the surface will be rising up to fill the lower half of his field of view, and the sky will take up the top half. There may be a band of convergence sandwiched between the two, where we just cannot see that far across the surface, the limit of our vision across the surface. Here's a similar example. The white line is the camera's eye level, and the yellow line is the eye level of the person in the photograph. And so he will be looking at a horizon at his eye level, not the horizon that we see at our eye level. Of course, we cannot know if the camera taking this picture was perfectly level, but we know for sure that the surface would never rise up as high as the yellow line. We do know that the surface and the sky always appear to meet right in the middle when we are looking directly ahead. This shot is a great example of how a photographer can play with perspective and change the level of the horizon line. Here we see a white line showing the camera's eye level, but here the photographer has deliberately put the edge of the lake level with the subject's eyes. And we know that if the cameraman moved his camera up or down, then that would put things out of whack. So regardless of any arguments about the minuscule differences in degrees that might indicate we are looking down a curve or into a bulge, what we must take into account, what has to be considered, is that when we are looking straight ahead, when we are flying level in an aircraft, we see the surface always rise up to create what appears to be an edge in the center of our vision. Of course, you could argue that when you get very high, then you do see an apparent drop in the horizon, but at the same time, we do not ever see a curve from side to side. And of course, the higher you get above a level plane, eventually you will be seeing more sky than the earth, But when we are relatively close to the ground, and that could even be a few kilometers up in the air, so our vision is split in two halves, the top half and the bottom half, the sky and the surface, and they always meet pretty much in the middle. It's simply our personal perspective on things. So, Fred is out walking his dog, and we are looking through his eyes. We see a green pasture coming up to eye level, and we see a chemtrail-free sky of fluffy white clouds coming down to the eye level. So we can see from this that Fred has a 4D perspective. He has the horizontal going left to right. He has the vertical going up and down. He also has depth of field, giving us an idea of the distance across the vista. But also what we instinctively know is that the height of something in the sky, or the apparent height of an object in the sky above the horizon, will give us an idea of how far away that object is. If, for example, a low-flying aircraft flies overhead, as it gets farther away from us, it will appear to get closer and closer to the horizon. But we also know that it will never go below the horizon. It will just disappear into the distance, just become too far away to see. And even if we whipped out a pair of binoculars or a telescope, we might be able to bring it back into view, but there would be ultimately a limit to how far we could see that aircraft, just because of the density of the air and the molecules and the dust and the haze and temperature differences and all sorts. And yes, of course, someone is going to bring up the argument that, well, if you're talking about the sun doing that, why doesn't the sun get smaller? Well, often the sun does shrink in size before it hits the horizon, and if we were on that aircraft, we would see the sun for longer and we would see it shrink a little bit more before it hit the horizon for us on the aircraft, our personal perspective, our eye level from the aircraft, which would still give us a horizon at our unique eye level in the sky. Nevertheless, the sun does often appear to hit the horizon while it's still quite large. This is simply because, from our earthbound perspective, we cannot see very far across the surface. We see maybe a few kilometers across the surface, but as you can see in this picture here, the clouds are much, much further away than we can see across the surface. And that's where the sun goes, and it's large anyway. It's about the largest thing around, so we don't see it change that much in size. But it will never ever go below the horizon. It simply goes beyond the horizon, and then when it is at the vanishing point is when it starts to shrink. And that's what we see every time we look at a sunset. And just for the record, I know that what I've illustrated here and what I am describing does not exactly match, but you get the point. Because when you go and look for yourself or look at close-up footage taken by people with very good cameras, you will see that the sun sets by going beyond a band of convergence at the horizon. It never goes below the horizon. Anyway, let's look at the fourth dimension of Fred's field of view here. We have the depth of field, but we also have the apparent altitude of things that he might see in the sky, giving us an indication of their distance. This is something never accounted for in the geometry of the globe. It is completely ignored, but it is something we instinctively know, but seems to have been conditioned out of us when we start trying to put the Earth and the solar system in an external frame of reference. So this is what we've been looking at here. We've been looking at Fred's internal frame of reference, his frame of reference, but the shots beforehand showed us that when we look at someone else looking at a horizon, we are looking from an external frame of reference. So it's very important to understand or to remember whether we are looking from our own eyes, through someone else's eyes, or what we expect to see through someone's eyes from an external frame of reference. So what I mean by this is Fred can be looking at 3 stars in the sky, 1, 2, 3, from the ground up. And this can be interpreted in a number of ways. The first star, the one lowest to the horizon, in Fred's eyes, could be the furthest star away. Star number 2 is a little bit closer, and star number 3 is even closer. So if we overlay a perspective grid on top of this landscape, we can see how we have to see the flat Earth. This is the perspective we have to look at the flat Earth. Yes, ignore all the science that tells us stars are billions of miles away, because no one can prove it anyway. It's just a mathematical arrangement. But when we see objects in the sky which we cannot possibly measure the distance to from the ground with no other reference, we can see it like this, even if we don't understand how it works. What you see is what you get. Star number 1 is close to the horizon, so it's far away. 2 is higher up, so it's closer to us, and star number 3 is even closer to us, so it's higher in the sky. But we do know that even though you could interpret these stars as being in a vertical arrangement above the same spot on the Earth, this is not the case, because as we got closer to them, or as they went overhead, they would appear to become closer together. So that's not the case. So when we try to illustrate what Fred sees from an external frame of reference, this becomes arbitrary. It's very difficult to correctly interpret what he sees. First of all, despite what we are continually told in our formative years, we simply do not know whether the Earth is moving or whether the stars are moving. But when we try to illustrate what Fred is seeing from this two-dimensional external frame of reference, we run into problems. If we illustrate it just as he saw it, we have the stars appearing to go down diagonally towards the horizon. And when you do illustrate it this way, from a 2D external frame of reference, not taking into account the depth of field or the apparent altitude or height with distance, then we can say that you're on a ball rolling past the stars as they come up over the horizon. Or you could say that the stars are rolling over our heads as we remain stationary on the ground. But this is simply the wrong way to represent Fred's four-dimensional perspective with depth of field and objects in the sky being close to the horizon because they are further away, and high in the sky because they're closer. In fact, you could argue that the stars are in this kind of arrangement. How would you be able to tell? The point is, though, that we have completely ignored Fred's four-dimensional perspective from this two-dimensional perspective. And we've had to make a choice based on the foundations of the model, the heliocentric model. But what we have to do to truly represent Fred's multi-dimensional perspective from the Earth in this two-dimensional external reference frame is to bring the stars up to the same height above the Earth. And we know that when Fred looks at star number 1, it's going to be high in the sky, a high altitude. And star number 2 is going to appear lower because it's further away. And star number 3 is going to appear much closer to the horizon because it's even farther away from Fred. This is perspective, but this is not how it is represented in two-dimensional external frames of reference. But we do know that this is a much truer representation of what Fred sees, or anyone sees, because as the stars travel overhead, we will not see any difference in the apparent distance between them. They remain fixed in their constellations. We also know that it's impossible to predict with any certainty the distance between Fred and the star. It could be very close, it could be very far, all on the same line of sight, at the same apparent altitude, from Fred's perspective. So this is why when someone like Voice of Reason comes along trying to defend the globe, talking about the relative angles of the moon and the sun and how that would be impossible on a flat Earth, what he is not doing is taking into account the four-dimensional perspective of Fred on the ground, and how a setting sun on the flat Earth is a sun maintaining a consistent height above the flat Earth, but in our eyes it appears to sink to the horizon. So when he then demonstrates that the angles from his two-dimensional external frame of reference do not match what we should see according to the globe Earth way of looking at things, he is completely misrepresenting the way we actually see it. And when we see the angles between the observer on the ground, the moon and the sun represented in this external reference frame, he's using angles from his two-dimensional external reference frame, but he didn't put the observer into the external reference frame. He did not put in the angles at which we see the sun set. If the sun and the moon are on opposite sides of the flat Earth, then from the observer's perspective, that sun has already sunk below the horizon. You simply cannot debunk the flat Earth by using the false external reference frames that are used to illustrate the globe. And this is why the globe is wrong, because we are constantly being told to consider the globe from an external two-dimensional frame of reference, when really what we see is a four-dimensional internal frame of reference, and that is never ever translated into illustrations of the globe. So, globeheads, you're just two-dimensional thinkers. When flat earthers talk about a flat Earth, we're not talking about a two-dimensional plane. We are talking about a multi-dimensional plane with bumps and rises and hills and mountains and lakes and perspective. If you're going to debunk the flat Earth, then you must debunk it from the observer's real perspective. Thank you very much.